All right, so the plan for today is to just continue with chapter 4, and we should finish up 2x2 applications and a couple problems here. 2x2 meaning 2x2 linear systems, so two variables and two equations. And then moving on to 4.4, 3x3 systems, so three variables, three equations. We'll look at a couple examples of those. We'll see that 3x3 systems behave pretty similarly to 2x2 systems. But we want to approach them more algebraically than graphically. They're a little bit harder to graph, certainly not really feasible to graph on something like a TI-83. We're skipping 4.5 and 4.6, solving with matrices and determinants. Basically, the reason is that to have a proper discussion of matrices and determinants would require an awful lot more background. And just throwing this new idea in here that doesn't seem to really make any sense and just completely comes out of left field doesn't make a whole lot of sense to me. It's just saying, here's another way to solve linear systems. And don't get me wrong, this is incredibly important stuff, but we just don't have the background to appreciate what's actually going on in something like Cramer's rule or solving with matrices. So it always puzzles me a little bit why it's included in intermediate algebra textbooks. So we are going to skip those and then start on 4.7, and that's where we'll pick up in next class, graphing systems of linear inequalities. This week, remember, we have the Unit 1 exam. The material is chapters 1 through 3. Sample exam is posted. Recall that there's no Proctor U for this first exam. And again, don't wait until the last minute to take the exam. I would recommend that you take it, plan to take it no later than tonight. And that way, if anything does go wrong, you have a good bit of buffer to get that worked out. All right, so any questions before we get started? Right. And the quote of the day today is that difficulty tends to increase non-linearly with complexity. So, one kind of example of this is, say we have just a linear equation in one variable. Maybe on both sides of the equation, it has some parentheses. There's some simplification we can do on both sides. We probably want to, if we're starting at, say, this level of complexity, we want to decrease the complexity by, say, taking each side individually, multiplying out, simplifying, combining like terms, make it as simple as possible. And then we do one equation solving step, which tends to increase the complexity a little bit. And then we do the same thing. We simplify, do another equation solving step, and eventually we have completely simplified the problem. This is going to be much easier to simplify at each step than to make it really complicated and then try to come down this other side of this hill, right? If the problem ends up being like twice as complex or having twice as many steps that you need to do to solve it, it's probably a lot more than twice as difficult. This also actually kind of applies to linear systems. Roughly speaking, the number of operations we need to do to solve an n by n linear system looks something like n cubed. So if I double the size of the system, if I go from a 2x2 system to a 4x4 system, I have like 2 cubed, or 8 times the amount of work to do. So 3x3 linear systems, are going to require quite a bit more work to solve. Now, the strategies are similar, so it's not very, conceptually difficult work, but it's just a lot of operations that we just have to be careful with and keep track of. So this applies in math. Basically, before you go and make a problem more complicated, try to make it simpler first. And then, if you can simplify and then complexify, that's better than making it more complicated first and then trying to simplify on the other side. This also kind of applies to life. If you have some, challenging or complex life situation coming up, remove as many variables as you can from that situation, right? If you're moving across country or moving to another country or something like that, ask yourself, okay, what are things that I can take off of the plate, right? Like, can I sell some of my furniture and not have to deal with trying to figure out how to get that across country while I'm also trying to figure out job and living situation and all of that, right? And there will be furniture at IKEA there that you can buy, that kind of a thing. So can you decrease complexity before you increase it instead of, increasing it and trying to ship all this stuff across country and ending up with a whole house full of stuff, and then you're trying to sort through it and chip away at it over time. So I think this applies more generally than just in math, but we certainly see the applications in math. Okay, so we have two 2x2 systems that we're going to look at. The first one looks familiar because I messed it up last time. So as I said, the more operations that we end up doing up in these systems, the greater chance there is to make some silly error. And that's exactly what I did. I made a silly error. So we started off, we got this system of two equations and two unknowns. This was the Bob's meal with chicken and rice and targeting a certain amount of protein and a certain number of calories, which I'm trying to select here, but it keeps putting my little pop-up in front of where I'm trying to select. Targeting a certain number of calories and a certain number of grams of protein for this meal. So that was the system we came up with. We talked about the details of where to get that from last time. We also have the practical constraint that, well, I mean, maybe mathematically we solve this system and it says, you want -2 ounces of chicken and 8 ounces of rice, but that's not practical. So chicken and rice need to be non-negative. We need to have only non-negative amounts of each of those for this to be an actual practical solution. And what I said is I wanted to clear my decimals in the second equation, so I multiplied everything by 10, and I ended up multiplying 5.3c to 53c. That looks good. 35 to 350, that looks good. But I multiplied, for some reason, 0.8. I wrote down 80, and that should be just 8. So that was the error last time. So now that we have that error fixed, let's go through and do this. And we also have the benefit today that the calculator is back up and running. So it was glitching out a little bit last time. So, but looks like it's working well this time. Okay, so let's work through this system, right? The kind of first big step was creating the system from this paragraph, from this explanation here. Let's work through solving the system. And again, we could use addition elimination method. We could use substitution method, whichever one you feel like using. Let's use substitution. I don't think there's a whole lot of benefit one way or the other for this problem. So if we use substitution, maybe we can solve this for R in terms of C, the second equation. I'm just picking that one because it has the nicer coefficient. I'd rather divide by 8 than one of these other numbers. So R is going to be 350 minus 53C, all divided by 8. And then I'm going to plug that into equation 1. 67C plus 37R equals 550. I want my R in there. So I'm just going to replace that R with all of this stuff. It's not the nicest stuff to replace it with, but it is what it is. And that equals 550. Okay, so what can I do now? Well, I see that I have some C terms. I have some parentheses that I can simplify. I have a couple of choices here. I could multiply everything by 8. If I do that, that's basically just going back to the addition elimination method anyway. I could try to distribute and keep the fractions. I think I'll probably just multiply by 8 to clear the fractions. So I have 8 times 67c plus 37 times 350. The over 8 goes away from this term because I multiplied by 8. Then I have minus 37 times 53c and equals 550 times 8. So I think I've got everything. I multiplied my 8 through to everything. It's easy to forget to multiply on the right side in any of these, whether you're doing addition elimination or just solving the linear equation. But it looks like everything is good. So I have 8 times 67 minus 37 times 53 c, and that's equal 550 times 8, and then minus 37 times 350. And let's come over here and figure out what these two numbers are. So we have 550 times 8 minus 37 times 350. That gives me negative 8550. And what's my coefficient of C? 8 times 67. Oh, 8 times 67 minus 37 times 53. And that gives me negative 1425. So then C, of course, is going to be the ratio of those. So it's going to be 8550 divided by 1425. And that turns out to be 6. And I think this was in ounces, right? Yeah, calories per ounce and grams per ounce. So we want 6 ounces of chicken. And then how much rice do we want? Well, we can just plug our chicken answer of 6 back into this equation for the amount of rice. So I need 350 minus 53 times 6. That's my numerator. I'll hit enter and then divide by 8, which gives me 4 ounces. Let's say 4, not a 9. 4 ounces of rice. So 6 ounces of chicken, 4 ounces of rice would get us this this goal here. Any questions on that? I think that's one of the most challenging things with linear systems is there's just so much going on and so many little operations you need to do. It's so easy to just make, a silly mistake like I made there and just move 1 decimal point one place too far, and I was getting some kind of crazy negative number for the amount of chicken, and I knew that wasn't right. So and it's also one of those kind of errors that it's hard to see, right? If you're looking back through your work, like catching little mistakes like that is difficult. Catching conceptual mistake, is sometimes a bit easier. You're like, oh yeah, I made this, this kind of silly error or this conceptual error that's maybe sometimes a little easier to catch than, if you've done 30 or 40 or something small operations, which one of those went a little bit awry is kind of difficult. So that's one of the big challenges in linear systems, I think, is just keeping track of everything. And that's going to be an even bigger challenge in 3x3 systems, just because there are more operations to do. Okay, so let's look at this last problem in 2x2 systems. So again, we'll take this narrative, we'll set up a 2x2 system and then solve it. These aren't the nicest numbers, but we don't always get to deal with super nice numbers. We do see that we're dealing with an interest rate problem here. OneNote just tries to be so helpful in connecting all of my lines together. So our interest rate basic formula for simple interest is I equals PRT. Principal, the amount owed, times the interest rate, times the number of time periods. Okay, so this says Josie owes 65,800 in student loans. Interest rate on federal loans is 4.5%. Rate on private bank loans is 2%. That's very unlikely to be true in a real case. Your private loans are almost always going to be higher than federal loans, but the total interest she owes for 1 year is 2753.50. Set up a system and find the amount of each loan. Okay, so let's call the two loan amounts F for the federal amount. In other words, the principal for the federal loans, and for private, I kind of don't want to call it P because I've already kind of used P. Maybe I'll call it B for bank. The amount that's owed to the private bank, that's like the principal that's owed there. So we have like two different principal amounts, one owed to the federal government and one owed to the private bank. So I know that the combination of them together is 65,800. So that just comes from the total that she owes being the sum of what she owes to the federal government plus what she owes to the private bank. And we have another system here, or another equation, another constraint for this system related to the interest. So we're not given an explicit time period here. I mean, it says for 1 year, and it just says the rate on the loans is 2% or 4.5%. So we're presuming that that's 1 year. That's a pretty safe, reasonable assumption here. This is a little bit of a side note. In math, when I write problems, I try to be extremely explicit about everything. But that's not always the case. In real life, a lot of times you have to make reasonable assumptions or presumptions. You have to presume that, say, an interest rate is an annual interest rate, something like that. Right. Most things in life, there's going to be more ambiguity than in math problems written by math professors. We tend to be very, we tend to be very precise about the way that we say things, at least ideally, especially when we're typing something up or taking care to write something out. So I think this is kind of a side note, but I think one of the career skills, whatever career you're going into, is kind of understanding there's a base set of assumptions in that career field, and what are those assumptions? When can you make such assumptions? When somebody communicates something to you and it's not clear, like when do you ask for clarification versus when do you take the ball and run with it? And I think that's something that you just have to kind of find out with experience a little bit. But that's one of those soft skills, right? It's like you don't want to be the employee who's always going to the manager every time they give you a project, and 10 times each day you've got some little tiny question. I don't know if any of you watch Seinfeld. That's probably like ancient history by now, but there was an example where Jerry Seinfeld, the main character, hired this guy to kind of renovate his like little kitchenette area. And every little thing the guy was asking him, do you like, these knobs or those knobs? Do you want me to do this way or that way? And Jerry's like, well, you just make a decision, right? And then Jerry comes back and it's like completely different, like, completely off the wall. He like closed everything in and it just looks crazy. So anyway, being able to know what decisions you should make and what decisions you should, push up the flagpole is, I think, one of those soft skills. So I guess little aside, little tangent, but I think we are safe in making the assumption that this is an annual rate. All right, so if the interest rate for the federal loans is 4.5%, then the interest charged over that year is going to be 0.045 times the amount owed. And the interest rate on the private bank loans is 2%. So the amount of interest over that year is going to be 0.02 times the amount owed to the bank. So here we're taking time to just be 1 year, and the amount of interest is principal times rate. This is the number of dollars that we will owe the federal government in interest for that year. This is the number of dollars that will owe the bank for that 1 year, the private bank. Why am I harping on this so much? Well, because this is 2753.50 is also the number of dollars that we owe the combination of both of them. Could we have set this problem up differently? And could we have said, you know, the interest rate for the year is, well, let's see what it would be. 2753.50 over 65,800 is 4.18%. The kind of her aggregate interest rate for the year was 4.18%. We might be tempted, if we were given this 4.18% instead, to do something like this left-hand side equals 0.0418. And that wouldn't be correct because we see we have amount of interest owed in dollars on the left side, and we just have a rate, a unitless quantity on the right side. So we could have had a similar problem phrased this way. And in fact, we did have a problem that was phrased kind of like this with the acidity, right? We wanted whatever 30 fluid ounces of a 6.2% acid. Well, that right-hand side had to be 0.062 times 30. It wasn't just 0.062. So it's important that we, when we can, we track our units. That really helps keep things straight, right? If I tracked my units, I would realize if I was in the green problem, I'd realize I had unitless on the right, just the number 0.0418, but I had dollars on the left. Well, I need to take 0.0418 of my total principal, 65,800. So tracking our units when we have units to track that are sensible, that is definitely a good idea. Now, in this particular version of this problem, we don't see that, so it's a little more straightforward, but I wanted to point that out, just that we checked that the units match, and sometimes that is a very important check. In this case, things worked out a little more naturally, a little bit more nicely, but they don't always. And in some of the problems on the homework, you know, when you're dealing with percent solutions and so on, that is something that you have to be careful of. Make sure that you have the correct units on the two sides of the equation. Okay, so we want to solve this system here. Since I did the last one by substitution, let's do this one by elimination. Maybe I'll take equation 1 and multiply it by something, let's say, to make b go away, since that has the slightly nicer coefficient. So I'll take negative 0.02 times equation 1, gives me negative 0.02f minus 0.02b equals, and this is going to be negative 0.02 times 65,800. So 0.02 times 65,800. So negative 1316. And then we just copy equation 2 down. We don't need to change that one at all. So 0.045f plus 0.02b equals 2753.50. So now I still have two equations and two unknowns, but now I can add these together. And I notice that my minus 0.02b plus 0.02b goes away. My f variable has a coefficient of 0.045 minus 0.02, or that's 0.025. And my right-hand side, let's see what that is. 2753.50 minus 1316, 1437.50. And then I'll divide that by 0.025. So this gives me 57,500 for the amount that I owe the federal government. And then the amount that I owe the private bank is just 65,800 minus F, or 65,800 minus 57.5, or that's 8,300. And these are, of course, in dollars. Okay. So getting the solution wasn't all that terrible. Wasn't that bad because mainly because f plus b equals 65,800 is a pretty nice equation. Even if we were to do substitution, that's an easy one to solve for one of the variables in terms of the other. But I think the tricky part here was just making sure that all of our units were right in the second equation. Now, in this problem, again, it was a little more straightforward. You know, even if you didn't check the units, you probably still would have got it right. But in other problems where the kind of right-hand side, so to speak, is given more in terms of the percent, you've got to be a little careful. You've got to be especially careful and just make sure that we're comparing, you know, apples to apples or dollars to dollars in this case, or acidity to acidity or salinity to salinity. So there's a couple of problems in the homework like that, and a problem or two that we've seen before that was like that. Okay, so moving on to 3x3 systems. The book makes kind of a big deal about all of the different possible geometries for 3x3 systems. I think that goes a little bit too far. Again, I think that kind of, you know, tries to touch on some linear algebra stuff, but it's one of those things like I don't particularly see the reason to go to that extent when we don't have all of the, you know, it's a little bit like you throw a wedding and you like want to invite this next circle of friends, but you have to kind of invite the whole circle of friends. You don't want to just invite like two people of that circle of friends out of like 20. I feel like it's almost the same thing. It's like we're trying to like tease a bit of linear algebra, but it's not really enough for it to make sense, and we don't have enough background for it to make a whole lot of sense. So my comments on 3x3 linear systems are essentially that, number one, if you find this stuff interesting and you go on with your mathematical career and, you know, take the calculus sequence, you might take a course called linear algebra, and that deals with all of this idea of linear systems in a lot more detail. Linear systems are incredibly important. They're quite annoying to solve by hand most of the time. We like solving them on the calculator or computer because of that, because calculators and computers are good at doing lots of tedious operations very reliably and very quickly, and that's something that we're not good at. And nicely enough, the kind of general ideas of 2x2 linear systems pretty much generalize to n by n linear systems. So 3x3 linear systems, we could end up in a scenario where we have no solution. We could end up in a scenario where we have infinitely many solutions. And we could end up in a scenario where we have exactly one solution. Those are the possibilities, just like 2x2 systems. We have three equations and three unknowns. A solution is an ordered triplet, like an ordered pair, but an ordered, you know, pair plus one extra, x, y, z. that when I substitute it in, simultaneously solves all three equations. So I'm looking for an XYZ that when I substitute in solves all of these. I could maybe in theory use a graphical technique to solve this. Again, looking at those planes and all of that that the book talks about, but in practice, nobody does it that way. I would need a three-dimensional graphing utility. Some calculators have them. You can also find them online. So you could solve it graphically with the technology we have these days. But for these, it's much more practical to just use either substitution or elimination method. And typically what we what we would like to do in an efficient strategy is basically use elimination method a couple of times to get to a situation like this. And then from this point, we use substitution. We call it back substitution. So I kind of eliminate using my first equation to eliminate the x variable in the second equation, and then using those two equations to eliminate the x and y variables for the third equation. And then I back substitute. I solve the third equation for z, which now I can see that the third equation is a linear equation in one variable. I can solve it for z, get z equals number. And then I have 6y plus number equals 10. I can then solve that. So plugging that z in gives me one equation and one variable for y. And then I have y and z. I plug those in. I'm having a lot of issues selecting things properly. Plug those into the first equation, and that gives me one equation, one variable for x, and I solve that. So that's kind of the process in some kind of optimal sense. This, roughly speaking, this process is called Gaussian elimination. So you kind of eliminate going down, and then you substitute going back up. But you know, when we have that available to us pretty easily, we might take that approach. But we're not going to take an approach that's that formal. We're going to take an approach that's a little more just kind of ad hoc. But in this case, I do notice that one of my equations is super easy to solve. I see that 7z equals 14. Whatever my solution is, x, y, z, it has to satisfy this equation. This immediately gives me my constraint on z, that z has to be 2. But now, in light of the knowledge that z equals 2, I see that equations 1 and 2 become a little simpler. And in particular, equation 2 is now just a 1-by-1 equation. It's just a linear equation in one variable. So now I have 6y plus 4 equals 10. Subtract 4 from both sides, 6y equals 6. Y equals 1. And now I see equation 1 becomes even simpler still. X plus 3 times 1 minus 2 equals 5. Or 3 minus 2 is 1. Subtract 1 over x equals 4. So my solution x comma y comma z equals what? 4 comma 1 comma 2. So that is the one and only point that simultaneously solves all three equations. So if I can get to a system like this, we can see that it's pretty easy to solve. All that I really had to do was solve 3 linear equations in one variable. That's much easier than solving a 3-by-3 system. Okay, let's take a look at this one here. 4x minus 2y plus z equals 3, 2y plus 3z equals 13, and 5y minus 7z equals negative 11. Now, something I notice here is that I only see x in the first equation. The second and third equations, it's really not cooperating with me to select things for whatever reason. But the second and third equations, if I look at those as a pair, well, that's actually just a 2x2 system that's kind of hiding in this 3x3 system, right? In a sense, we had like a 1x1 system hiding in here. But now we have these two equations that pair up to make a 2x2 system. I can actually just pull those off to the side and solve those. I have two equations and two unknowns, y and z. I should be able to solve that 2x2 system more easily than I can solve a full 3x3 system. Two y plus 3z equals 13. 5y minus 7z equals negative 11. And what could I do here? Well, I could do substitution. I could solve one of these equations for one of the variables, plug into the other. Let's do the addition elimination method. For this one, this is going to be a little more challenging. I can't just multiply one of my equations by one number and get something that's going to cancel out. So maybe I'll choose to cancel out, let's say z. I know that I ultimately want to end up with opposite signs, and z already has opposite signs. Right, again, I'm thinking from the context of I know I've got to do a lot of operations. I know that if I multiply through by a negative, the chance that I miss a negative or forget to flip a minus sign to a plus or a plus to a minus is decent. So maybe I will target the variable that already has the opposite sign, so I only need to multiply by positive numbers. So if I look at 3z and minus 7z, what do I need to multiply each one by to make them cancel out? Well, I need to multiply the 3 by 7 and the minus 7 by 3. So I'm going to multiply equation 1 by 7 and equation 2 by 3. So equation 1 multiplied by 7, this gives me 14y plus 21z equals 7 times 13. That's 70 plus 21. I think that is 91. And equation 2 multiplied by 3 is 15y minus 21z. And negative 11 times 3 is negative 33. Now when I add these together, I see that my 21z's go away. I have 19y and 91 minus 33. That's what? 61 minus 3. That's 58. And yeah, I thought I had a nice solution to this, maybe not. 58 over 19. I might have, I thought when I created this problem, I had a nice solution to it, but seems like that didn't work out so nicely. Let me just double check my arithmetic here. Did I actually copy everything over correctly? Yeah. Yeah, it looks good. So, um, all right, so y equals 58 over 19. Not the nicest solution. I had intended for it to be a nicer solution, but didn't quite work out that way. And then I can find z, say 2 times 58 over 19 plus 3z equals 13, say from equation 1 up here. So what does that give me? 116 over 19 plus 3z equals 13. And z is going to be 13 minus 116 over 19, all divided by 3. Or what's 13 times 19? 247 minus 116. So that's 131 over. And then 19 times 3 is what, 57? So that's what z is. And now I've solved my 2x2 system for y and z, my kind of embedded 2x2 system. I can come back up to equation 1, and I have 4x minus 2y plus z equals 3. And so I see that x is not the nicest answer in the world, but that's what x turns out to be. And we probably could simplify that fraction, but I will leave it there. Wonder if I got a sign wrong when I made the problem. Okay, and then this last example for 3x3 systems, we have a full 3x3 system here. Each of the three equations has x, y, and z in it. We also see that we have a lot of fractions. So the first thing I'm going to do is, again, I don't want to increase complexity before I decrease it. I want to decrease complexity first. So the first thing I'm going to do is clear all the fractions. I'll multiply equation 1 by 3. I'll multiply equation 2 by 6. And I'll multiply equation 3 by 6 as well. Just clearing all my fractions. So I have 3x plus y minus 6z equals negative 3. Equation 2 multiplied by 6 gives me 2x plus 6y plus 3z equals 0. And equation 3 multiplied by 6 gives me 3x plus 2y minus 3z equals negative 6. Just going to double check that I got all of my signs correct and did all of my cancellation correctly. All right, looks good. So now my goal is to try to identify a variable that I can get rid of. I would like to go from a 3x3 system to a 2x2 system. I want to identify a variable I can get rid of fairly easily. And I actually see that the coefficients of z seem to kind of work together all nicely. So for instance, I could take equation 2 and equation 3 and add them together, and the z's immediately go away. And I can maybe take twice equation 2 and add it to equation 1, and the z's will go away there as well. So let's start with equation 2 plus equation 3. When we add equations 2 and 3 together, what do we get? We get 5x plus 8y equals negative 6. My z's went away. So this is one of my equations of two variables, x and y, and I've eliminated z. I need a second equation in x and y, and I don't want to use these same two equations, 2 and 3. I need to use some other combination of equations. I need to bring the information from equation 1 in somehow. So I think what I'll do is I'll take equation 2 times 2. That'll give me a plus 6z. And then add equation 1 to that. That's a minus 6z. As a side note, I could have pretty easily eliminated the y's instead. It would have been, a little bit more work, but not much. The x's would have been kind of annoying to eliminate because the 2 and 3 don't really work together very well. I'd have to multiply one of them by 3 and the other one by -2, and that's a lot of multiplication to do. Okay, since I have an extra step here, I'm going to write out an intermediate step. So I have equation 1, 3x plus y minus 6z equals -3. And I'm going to write out twice equation 2. So I have 4x plus 12y plus 6z equals 2 times 0 is 0. And now I'll add these together. So I have 7x plus 13y, my z's go away, equals -3. There's my second equation in 2 variables. So I now have 2 equations and 2 variables to deal with. Okay, again, I can use substitution if I wanted to. Certainly could go that route. I could use addition elimination. Let's use addition elimination. Maybe I'll call this A and this B, these 2 equations. And maybe I'll choose to eliminate x. I think it's about the same either way, and x has the slightly smaller coefficients. So I'm going to multiply equation A by, let's say, -7. And I want to add to that equation B multiplied by +5. So it'll give me a -35x, a +35x. They should go away. So A multiplied by -7, -35x minus 56y equals +42. And equation B multiplied by 5 is plus 35x plus, what is that, 50 plus 15, 65y equals -15. I add these 2 together, my x's go away. I have 65y minus 56y, I think that is 9y. And 42 minus 15 is 32 minus 5, or that is 27. So y has to be 3. So I've got one of my 3 answers now. And as kind of an aside, right, I have like 9y equals 27 is one equation. I could think of this being a second equation and say this being a third equation. At this point, once I get down to 9y equals 27, I don't think I explicitly said this, but I'm effectively in this kind of a situation now. Right, I have this equation, one equation and one variable. I have an equation, say this one, or you could use the other one. I have another equation in one more variable. So once I solve the one below for y, this is one equation and one variable. And then I could pick whatever one of these I want up here. That's another one equation and one variable after I know what y and z are. But I get y equals 3. Let's maybe make this green. We're going the other direction now. And then I have 5x plus 8y, 8 times 3 equals -6. 5x equals -6 minus 24. 5x is -30, x is -6. So now I have y is 3, x is -6. And then I pick one of these equations up here. Maybe I'll go with this one of the equations with all 3 variables, just because it has a 0 on the right-hand side. That'll make it a little easier to solve. So I have 2 times -6 plus 6 times 3 plus 3z equals 0. Or I have -12 plus 18 plus 3z equals 0. So that's 6 plus 3z equals 0. 3z is -6. Z is -2. Okay, so these 3x3 examples we saw all had a unique solution. We can look at an application problem like this one here. And then I think next time we'll take a look at an example that has one of these kind of degenerate solutions, either no solution or infinitely many. Now for this system, I mean, I wanted to use something realistic so that you can see that you can actually use this for kind of interesting stuff. But the problem is the more realistic a problem gets, the more difficult it tends to be to solve. And you can see even these, problems that were created to be fairly easy to solve, fairly nice solutions, are quite a bit of work. So for this one, we're just going to set up the 3x3 system and we're not going to solve it. But I did give you the solution here. So here, Bob wants to plan a lunch consisting of rice, steak, and pistachios. He wants a total of 45 grams of protein, 20 grams of fat, and 60 grams of carbs in his lunch. This gives a total of 600 calories at a 30-30-40 calorie split. Note that fat is more calorically dense than carbs and protein, 9 calories per gram as opposed to 4 for the others. And we have the nutritional information for these 3 foods. And we want to set up a 3x3 system for the number of servings of rice, steak, and pistachios he'd need for his lunch. And then, you can put together a lunch. Again, presuming that the solution actually comes up with an amount of rice, steak, and pistachios that is non-negative, of course, and that we don't have one of these degenerate solutions where there's no solution, or degenerate systems where there's no solution. So I really have 3 constraints. I have one for protein. So the goal is 45 grams of protein. And that's going to be gotten from the combination of rice, steak, and pistachio. So that's 2 grams of protein per serving of rice times, let's say R is the number of servings of rice, plus 30 grams of protein per serving of steak times, let's call it S, the number of servings of steak, and then plus 20 P for pistachios. So that's one of our equations in 3 variables. We also need 20 grams of fat. So for fat, 20 has to equal, and very similarly, let 0R, or I suppose we could just not write that, plus 5S plus 45P. And then for carbs, we need 60 grams of carbs, and that's 46 grams per serving of rice times the number of servings of rice. No carbs in steak, not an appreciable amount anyway, and then plus 27 grams of carbs per serving of pistachios times P, the number of servings of pistachios. This would be our 3x3 system. At first glance, it doesn't look that bad to solve, especially because we're like missing a couple of variables, but it turns out that, just the numbers here don't work out super nicely. So you end up with like 5,000 and something over 11,000 and something, or, something like that. But this is the approximate answer. So you need about 1.1 servings of rice, 1.2 servings of steak, and 0.3 servings of pistachios, or for their serving sizes, that's about 6 ounces of rice, 4 ounces of steak, 1 ounce of pistachios. The other nice thing about this is if you can automate this by, say using a calculator or an online tool or something, you could, decide what 3 things you want for, for your meal today, what 3 constraints you want to satisfy, and then, figure out how much of each you would need. And then see if that's a reasonable, if it's like 10 ounces of steak and 1 ounce of rice and no pistachios, that's, kind of a silly meal. Um, but anyway, so you can, set up and solve equations. Uh, I didn't solve this by hand. I solved it using the calculator, or well, really using a programming language, and then got the fractional answer with an online tool. So that's the way that you would solve something like this, realistically, when the numbers don't work so nicely. But again, that's kind of, in my mind, that's outside of the scope of an intermediate algebra course. That's more for something like a linear algebra course where you're really digging into the details of, you know, the different types of systems where you have solutions and don't have solutions, what those solutions look like. So that's more for that kind of course in my mind anyway. Okay, any questions on linear systems? So that pretty much wraps us up. We'll do maybe one quick 3x3 degenerate system next time, and then move into section 4.7. 4.7 should go pretty quickly. And then we finish up chapter 4 and move on from there. Don't forget that the unit 1 exam is this week, so make sure that you get that done in the next, preferably by tonight. And yeah, so that was all I had for today. Are there any questions before we break for today?